Hello and welcome to an algebra tutorial video learning about exponential decay. So we've been working with exponential functions. If you remember right, we can write exponential functions in the form y equals a times b to the x power, or I can write them in function notation, f of x equals a times b to the x power. And both of them are exponential in that they have x in my exponent, my independent variables in my exponent. We're repeatedly multiplying by some number b, that's the base, and we have a starting value a, which is my y-intercept. But let's look at, an exponential decay, let's think about some things that we have going on here. We know that if I multiply a number by 1, multiply a number by 1, everything stays the same, right? It's one of the most boring things in math, stays the same. Anything times 1 stays exactly the same. So 8 times 1 is 8, 15 times 1 is 15, negative 2 times 1 is negative 2. Everything stays the same when you multiply by negative 1. Now, we also know that to get bigger, or to grow, let me actually bigger or get growth, that happens, we multiply by greater than 1. So multiply by a number greater than 1. That's when we get things bigger, right? That's when exponential growth happens, or we make our scale factor bigger. There's lots of places in math where we want things to get bigger. But that's nice, but we're very interested in exponential decay. That's what this video is about. So how do I make things get smaller? Well, if I multiply by 1 to stay the same, if I multiply by a number bigger than 1 to get bigger, to get smaller than, or in our specific example with decay, that happens when we multiply by a number less than 1, but still bigger than 0. So let's define now, we've got exponential decay. Exponential decay occurs when our value for b is less than 1, but it also has to be greater than 0. So b is between 0 and 1. B can't be 0. I can't multiply by 0. B can't be negative because that's not even an exponential function anymore. But b has to be a number between 0 and 1. So it's like a fraction. It's a small decimal. It's a small number. All right, let's take a look at an example here. Let's do a function y equals 80 times 0.5, I'm going to do 0.5 to the x power. So this is going to be an example of decay, exponential decay, because I'm multiplying by 0.5. That's between 0 and 1. And we're going to see some interesting things. We should see a function that is decreasing. So let's make a little table of values here. So my input value, x, and my y values. We'll do 0, 1, 2, 3, and 4. All right, so 80, that's my starting number. And my y values, I take 80 and I multiply it by 0.5. If I do it to the 0th power, 0.5 to the 0th power is 1, so my starting value is just 80. We know that. Now, if I put 1 in for x, 0.5 to the first power, 80 times 0.5 is just going to give me 40. If I put 2 in, 80 times 0.5 to the second power is going to be 80 times 0.5 times 0.5 is going to get me down to 20. And the pattern is I'm going to keep multiplying by 0.5 and decreasing by half every single time. If I went down to, when x is 5, I would get down to 2.5. And here we see we are definitely decreasing, which means we have exponential decay happening. All right, so there's a table. There's my function or my equation that I'm using. There's my table showing some points. I can easily see that things are decaying in my table. Let's pull up the graph and get another good illustration of what's happening. All right, there's a graph of my function. So we can see the points right here. There's 0, 80, graph of my table. There's 140, so I just plotted some of the points that I found. I even threw on an extra one here. We can see that it's approaching 0 as it gets smaller and smaller. My y values get closer to 0, so it's got a horizontal asymptote at a y value of 0. But this is what a graph of a decaying function looks like. Graph of exponential decay. It'll be curved. It always starts off big and it always shrinks down and then flattens off based on if there's a vertical shift, or it'll flatten off into 0 and decay, get infinitely smaller and approach the specific value. But there we go. There's a good example of exponential decay. It happens when our value for b is between 0 and 1. And there's all sorts of types of growth that we can use an exponential decay function to model, including radioactive decay, declining populations, anything that we're shrinking in value on a repetitive basis, we can use an exponential decay function.